Hi everyone, today I'm going to talk about a paper generating 360 video is what you need for a 3D scene. This work is proposed by Adobe Research, Yale University, Oregon State University, and published in SIGGRAPH Asia 2025. So here's the problem description. What we're going to do is to generate truly immersive, navigable 3D scenes from text. And here's the motivation. First thing is why this matters. Text-to-image or video models today mostly give us snapshots or short clips. For many applications, VR, AR games, or virtual tours, we really need a traversable 3D world. And about the recent research gap, the first one is many methods rely on single perspective view diffusion models and monocular estimation model and 2D painting, growing the scene just one view at a time. Even panorama-based models still do outpainting to fill missing regions. This will lead to the distortion point. And the second one is intuitively, we can use explicit representation, for example, 3D meshes or point clouds, but they are hard to get at scale, so training a text to 3D world generated directly on them is not practical. However, 360 videos are much more easier to capture and collect, and modern video diffusion models are strong enough, so it is very natural to combine them together. So, some work have tried to bridge this gap using panoramic images. That's a step in the right direction, capturing more of the scene at once, but they may still rely on outpainting. Imaging have a panoramic photo, but there's a big empty snapshot in the middle. Outpainting tries to fill it based on the edge. Sounds good, right? But you might get something plausible locally, and globally it often a mess. As you could see the video right here, the discontinuity happens, objects might distort, geometry gets wonky, and if you move your viewpoint, things could look really strange. This happens because our painting is inherently sequential, building on previous guesses, which doesn't capture the holistic nature of a real 3D environment. So what's the alternative? Instead of patching things together, just try to generate the whole scene in one go, ensuring everything lines up perfectly from the start. We need a way to represent the complete scene. Specifically, they use 360-degree panoramic videos so that they can capture reality with the camera moving through a space. And basically, it's a two-step training. First, they train a model to generate a video someone walking through in the virtual environment captured by a 360-degree camera. And then they take that video and reconstruct it into a 3D model, specifically a Gaussian splatting procedure, so that you can actually walk through it. So here's some related work. How do we turn images into 3D? Old school methods like meshes or point clouds have their place, but neural representations are where the action is. Nerve is a big deal. Representing things as a continuous function, but training per scene is slow, and rendering is computationally heavy, because basically what Nerve does is try to predict every single pixel during rendering using a single MLP. And then they come to 3D Gaussian splatting. It uses a bunch of Gaussian distribution to represent the scene, optimized for speed and memory. However, even 3D Gaussian splatting usually needs an optimization step to get the best results, which can be slow for large datasets. And then they turn to large reconstruction models, or LRMs. These are trained to reconstruct scenes with a single forward pass. They work like a one-shot 3D printer for vision. We just feed in a bunch of images once, and it directly outputs a 3D scene without per-scene tuning. They sacrifice a tiny bit of potential quality for massive speed gains. And next we will talk about 3D Gaussian splatting a little bit more, because LRM used in this paper also generate 3D Gaussian to represent the scene. So here's how 3D Gaussian splatting represents the scene. You may be quite familiar with triangle restoration in computer graphics, which is used to draw many triangles in the scene on the screen. However, instead of triangles, it's Gaussians. Here's a single trace Gaussian with a border drawn for clarity. It has several attributes. Position means where this Gaussian is located, and covariance means how it's stretched or scaled, and what color it is, how transparent alpha it is. So in practice, multiple Gaussians are drawn at once, so it could speed the rendering to speed the rendering up. Here's how it looks like each Gaussian rendering on screen. Here's the training procedure. The first step is to use the structure for motion method to estimate a point cloud from a set of images. This is a method for estimating 3D point cloud from a set of 2D images. This could be done with the command library. Next, each point is converted into Gaussian. This is already sufficient for registration. And only position and color can be inferred from the structure from motion's data, but it's not enough, and we still need to train it. The training procedure uses gradient descent because this procedure is totally differentiable. Reduce the Gaussian to an image using differentiable Gaussian registration and calculate the loss based on the difference between the rendered image and ground truth image, and adjust the Gaussian parameters according to the loss, and then we apply densification and pruning. If the Gaussian is small, clone it, otherwise split it. So let's back to the method. Basically, it contains a two-stage process. First, generation. They take a text prompt and feed it into their specified visual diffusion model. This model outputs a short video about 11 seconds long, showing a simulated walk through the described scene. Second, reconstruction. They take the video, chop it up into perspective views, and use CodeMap to figure out exactly where the virtual camera was in each frame. Then they fix these camera poses and views to the long LLM reconstructor to build a final 3D Gaussian splat scene. Because the input video is rich in detail and geometry consistent, the output 3D scene is also high quality, allowing for smooth, believable navigation from any viewpoint. So to start with, basically the stage 1 is generation. They fine-tune a pre-trained DIT model, which refers to diffusion transform model designed for text to image to text to video generation. And then specifically they fine-tune these models on their curated dataset, which contains 1.7 indoor 360-degree videos and 200K images. And then they use the mask diffusion loss to optimize their model. Basically, where the mask is 0, meaning exclude the person, and the loss contribution is 0. Finally, the model generates a low-resolution video, and then they use a GANs upsampler to get a nice resolution. Alright, so we have our high-quality clean-up 360-degree video. The next step is turn it into a 3D scene. So they take each frame and slice it up. They randomly crop 3 different perspective views from each frame, each with a 120-degree field of view and such resolution. This gives us so many views, and this is quite enough for the reconstruction tools like CodeMap, which requires these kinds of overlapping views. And then such consistency is what allows for reliable 3D reconstruction. Then they take these estimated camera poses and feed them along with a random subset of 32 views into the long LLM reconstructor. LLM is fast because it is just a feed-forward model, not iterative optimization needed. So it takes the poses and the image and efficiently builds the final 3D Gaussian splat scene. And then finally, a detailed 3D environment you can explore freely. So here's the experiments. To verify this two-stage proposed method perfectly, they conduct several experiments. The first one is to verify the video generation in stage 1. They compare it against the state-of-the-art 360-degree video generator at the time, 360 DVD. The model clips not only match the text prompt much better, like Coastal Castle example, but they also contain more realistic details. More importantly, notice the green box. It highlights the region that shows significant more parallax. And quantitatively, as shown in Table 1, their videos score better on standard metrics like clip distance, QLI, and VBench. So here's the final result, which is the second experiment. They compared their methods with several baselines. Lucid Dreamer on the top used outpainting. It looks okay initially, but trying to move around and you get blur, missing bits, and warped geometry. And middle columns are dream scene 360 and layer panel 3D, which uses a single panorama. They give you a 360-degree viewing, but if you stray too far from the initial position, the scene breaks down. Their method, bottom row, maintains fidelity to the prompt, high visual quality, and crucially stable geometry even when you navigate far away from the original camera path. So they also quantitatively evaluate their methods against several text-to-scene models. As you may see, their metrics perform pretty well. So about the application study. First, what if we only train on video data and skip the images? The video looks worse overall, and critically, the bottom part of the panorama gets messy and unrealistic because the max diffusion loss, it hides the bottom part of the video where the camera and hands are. And without any image data to provide supervision for those pixels, the model struggles to generate sensible content there. And about the second application study is the max diffusion loss. What if we just use regular diffusion loss, including the person in the calculation? The generated videos are riddled with the photographer and camera equipment, just like training data. Those artifacts block parts of the scene, making it impossible to reliably construct the underlying 3D structure. So here's the future work. Right now they only generate 11-second videos, but for really large complex scenes, we ideally want much longer sequence video. So that's one of the challenges for the future work. And second, panoramic videos, by their nature, spread pixels across a wide angle to capture the whole scene and ensure spatial consistency. They mitigate this with upsampling as we mentioned before, but ultimately a high-resolution video generator could be ideal solution to capture both broad scenes and the fine-grained details.